I will be discussing time dilation. It was introduced by Albert Einstein in his theory of relativity. There are two assumptions in the theory of relativity. The speed of light in the vacuum is the same for all observers, regardless of the relative motion or the motion of the source of light. And the laws of physics are the same for all observers in uniform motion relative to one another. According to relativity, two frames of reference that move differently from each other experience time differently, a process known as time dilation. As you travel faster, or if you are in an area with more gravitational force, such as another planet, time slows down. This means that not only does your watch slow down, but your entire environment slows down. Even your neurosynaptic thought rate slows down, causing you to not notice the change in time. In order to better understand time dilation, a better understanding of the four dimensions are needed. Most physicians label space and axes of x, y, and z representing left, right, back and forth, up and down. The fourth dimension is time. In order to simplify this even more, a two-dimensional graph with time here and then space are presented. This space is this entire representation. This graph right here is time and space with the speed of light. It is impossible to go backwards in time, and it is impossible to go faster than the speed of light. Therefore, all motion is above this speed of light graph. To put this into perspective, if you were to stay still in space, as in that dot, you would still be going up in the time graph of space and time. To correctly label this graph, on the time axis, you could have 1 year right here and 1 light year right here, which would mean that in 1 year, light travels 1 light year away. In order to further illustrate time dilation, I've drawn this example. Here's a clock which works through two mirrors and light bouncing back and forth between the mirrors. The time is distance divided by the speed of light. So the light traveling from right here to right here is one time interval. So for this example right here, we have a rocket ship going at 3/5 the speed of light with this contraption inside the rocket ship. Here's an observer at rest from Earth. The person in the rocket ship sees the light as he's traveling simply go straight up. However, the observer who sees the rocket ship moving at the same time and the light will see the light go at an angle towards this way and then back to here as the spaceship is moving. In order to further illustrate the previous example, I draw a simpler diagram. This D represents the distance that the light traveled in respect to the observer in the spaceship. The D prime represents the distance that the observer on Earth saw the light travel. VT equals the distance that the observer on Earth saw the rocket ship actually travel, and the T prime represents the time that the observer on Earth thinks that they saw the rocket ship travel. Since time equals distance divided by the speed of light, you can change that equation into distance equals c times time. This T prime equals the time in the Earth observer's own frame of reference, and the regular T equals the time observed in the spaceship's reference frame. You can then Pythagorize this example by doing d1 squared equals d squared plus vt prime squared. Substitute d prime for ct prime and substitute d for ct. Once you completely break down this equation, you get t equals t prime times the square root of 1 minus v squared divided by c squared. This is also called the Lorentz transform. This basically means that the time that the spaceship observer feels equals the time of the observer on Earth times the square root of 1 minus the speed of the ship divided by the speed of light squared. To put this equation into an interesting perspective, if you were to go 95% the speed of light for 10 years and then return home after that time period, Earth would have aged 32 years and you would have only aged 10 years. While spaceships cannot currently go fast enough to really make time dilation useful, in the future, if we could get anywhere near the speed of light, then it would make space travel extremely easy and make our time fractionally smaller to get from one place to another and back to Earth in a reasonable amount of time. The satellites that orbit Earth have clocks on them that are synchronized to match the clocks on Earth. Since time passes slightly slower on these satellites, the clocks need to be set for a slightly longer day. Therefore, time dilation comes in to calculate the exact amount of time that needs to be changed on these clocks. An interesting situation in regard to time dilation is the twins paradox. It goes as such. Rick and James are twins. When James is born, he boards a ship and travels at 3/5 the speed of light for 5 years away from Earth. He then immediately turns around and travels at 3/5 the speed of light back towards Earth. When he returns to Earth, James is only 8 years old, while his brother, who stayed on Earth, is 10 years old. According to time dilation, James should really be older than Rick. This paradox can be explained through a simple chart. Here are the years that pass on Earth, and here are the years in light years on the x-axis. This line represents this twin who goes into space because he goes 5 years away from Earth at 3/5 the speed of light. Notice that this is 3/5 of the 45-degree speed of light line, and then he goes back to Earth in a 5-year span. This straight up line to 10 years represents the twin that stayed on Earth. These lines represent a picture being sent from the twin in the spacecraft to the twin on Earth. The reason this is because communications at their fastest can go the speed of light. So the reason these lines represent the speed of light is that they're at a 45 degree from the horizontal. Therefore, at this point right here, when the twin on the rocket ship sends a picture to the twin on Earth, the twin will receive it when he is 2 years old. So the twin in the rocket ship will appear 1 year old, because when you go straight across, this point is 1.25, and when you multiply that by 4/5, it equals 1 year because of the Lorentz transform. So when you follow this pattern all the way up to 10 years, the twin returning to Earth will be 8 years, and the twin on Earth will be 10 years. The twin that stayed on Earth will be 10 years old. This phenomenon happens because the rocket ship experiences a change in perspective when it accelerates away from the Earth's gravity and when it has to make a turn back towards Earth. This causes two changes in perspective, which completely throws off the time dilation equation and makes the reverse true, where the twin coming back on the rocket ship is younger than the twin on Earth. A very popular experiment regarding time dilation is the Hayfield and Keating experiment. It involved flying planes around the world with a nano clock on it, and then comparing it to static clocks on the ground. The experiment proved that 273 nanoseconds were added to the clocks that flew around the world.